Write a balanced equation for the reaction between this weak base and water and write its equilibrium expression. All right, so here's our base, C5H5N, and we're trying to write an equation for the reaction between it and water. I'm leaving some space in case I need to balance it. It is a weak base, so that means I know that I need equilibrium arrows. So my first job is to predict the products of this reaction. And I talked about a couple different strategies that you can use for predicting products. One, I think the easiest one for me personally, is that if your reactant is a base, like in this example, one of the products of the reaction is going to be hydroxide, OH minus. If your reactant is an acid, which is not what we have in this case, but if it was, one of your products is going to be H3O plus. So if you know one of the products, that'll help you figure out what the other product is. The OH minus, since we know that one of our products is OH minus, that OH minus has come from most of the water, not all of the water. The water lost one of its hydrogens, and that hydrogen that it lost had to end up going over here to the base. So we're going to rewrite the base, C5H5N, but let's give it that hydrogen that it stole from water. And then also don't forget the water, when it turned into OH minus, it lost a charge as well. So that means, the water lost a charge. Where did the charge go? It went to the C5H5NH+. So there is the reaction balanced. Now we have to write equilibrium expression KB. This is going to be our products, OH minus times C5H5NH+ over our reactant, C5H5N. Don't forget you need to leave out water. It's not included in the equilibrium expression because it's a pure liquid. So now we're going to make an ice table. Just make the ice table. We're not actually going to do anything with it. We're just preparing it that we could use to calculate the pH of this solution. Our solution, it says HCN is 0.2 molar. Remember, we don't do anything with water in here. Initially, we don't have any products yet, so they're going to be 0. Our change, we don't know how much HCN is going to react, so we'll call it a minus X. Our cyanide is going to be a plus X. H3O plus is a plus X, and this is because the stoichiometry is the same all the way across this reaction. At equilibrium, we have 0.2 minus X. And remember, we're going to assume that X is much smaller than 0.2. So we're going to approximate that as being just 0.2. But for cyanide and for H3O plus, those are both going to be X. So that's the setup ice table. Now it wants us to calculate the pH of that solution. It's given us the Ka value, 4.9 times 10 to the minus 10. In order to calculate the pH of the solution, we need to figure out what the H3O plus concentration is, and that's represented by X in the ice table. So that means we need to write an equilibrium expression and solve for X. Cyanide times H3O plus divided by HCN. We are using X to represent both cyanide and H3O plus, so that's going to be X squared over 0.2 for the HCN. X squared is 4.9 times 10 to the minus 10 times 0.2, 9.8 times 10 to the minus 11, and then take the square root of that to get X. X is 9.9 times 10 to the minus 6. pH is the negative log of H3O plus. H3O plus is X. We just solved for X. So the pH of this is 5. Which two of the following can be combined to make a buffer? Remember, with a buffer, we're looking for the presence of a common ion. Like right away, I can see SO4 minus, or SO4, 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 SO3. That's not the same thing. KCl, that has nothing in common. So there, I've got it narrowed down to 3 right away. What is our other criteria for making a buffer? We cannot have a strong acid. Get rid of our strong acid. So that leaves us with these guys. We can't have a strong acid. We can't have a strong base. We must have a common ion present. More buffer questions. What is the pH of a buffer? That is 0.2 molar CH3COONA and 0.3 molar CH3COOH. So we got to use Henderson-Hasselbalch. Anytime you see the word buffer, you should be thinking, how can I use Henderson-Hasselbalch to help me solve this problem? Because this is our shortcut. pH equals pKa plus the log of the concentration of the base over the acid. So our first goal here is to calculate pKa. pKa is the negative log of the Ka, just like pH is the negative log of the H, and pOH is the negative log of the OH. Negative log of 1.8 times 10 to the minus 5 is 4.74. So we got that part figured out. Now we're ready to figure out the next part, the base and the acid. We have to know which concentration is which. What is the concentration of the base? What is the concentration of the acid? We've got to look at these two formulas and help us figure out which one is the base and which one is the acid. I was looking to see if maybe I'd already written up here in question 1 how we're going to determine base from acid, but I haven't, so we'll write it here. The base, now it's easier to start with the acid. The acid has 1 more hydrogen than the base. Because remember, an acid's job is to donate a hydrogen, so that means it's going to have an extra hydrogen. The base has 1 less hydrogen than the acid. So we're looking at our two formulas. This first one, that one has 3 hydrogens. And now we're looking at this one. This one has 4 hydrogens. So the one with the 4 hydrogens is the acid, 3 hydrogens is the base. The concentration of the base is 0.2. The concentration of the acid is 0.3. 0.2 divided by 0.3. Take the log of that and add it to 4.74. And that gives us a pH of 4.56. Here's a really similar problem. A buffer is made from H2CO3 and HCO3 minus, and it has a pH of 7. It gives us the molarity of the H2CO3. What's the concentration of the other part of this solution? Again, anytime you see buffer, you always want to ask, how can Henderson-Hasselbalch help me solve this problem easily and avoid having to use an ice table? So let's figure out from the Henderson-Hasselbalch which parts of this equation do we know. We know that we have a pH of 7. So I'm going to fill that in. The pKa is the negative log of the Ka. Negative log of 4.3 times 10 to the minus 7. The pKa is 6.37, so I'm going to fill that in, 6.37. And we have the molarity of the H2CO3. Is that the acid or is that the base? The H2CO3 has 2 hydrogens. The other solution has 1 hydrogen. So that means that the H2CO3 is the acid. So our 1 molar goes down here, and now we just have to solve this problem, which is going to be a little bit tricky because we're going to have to use the anti-log to get to that base concentration. 0.63, so first I just subtracted 6.37 from both sides. 0.63 is equal to the log of the concentration of the base divided by 1. We're going to take the antilog, so 10 to the 0.63 is equal to the concentration of the base divided by 1. I'm going to stop dividing by 1. The concentration of this base is 4.27 molar. That seems super high. It makes me want to plug everything back in and check my work because that seems like a really high concentration. But when I plug it back in, I end up with the right pH, so that is the correct answer.